anthem.
Bayang magiliw, dalas ng silanganan, alab ng puso, sa dibdib mo'y buhay. Lupang hinirang, duyan ka ng magiting, sa manlulupig. Di ka pasisiil sa dagat at bundok, sa simoy at sa langit mong bughaw. May dilagang tula at awit sa paglayang minamahal. Ang kislap ng watawat mo'y tagumpay na nagniningning. Ang bituin at araw niya kailan pa may di magdidilim. Lupa ng araw ng walhati pagsinta, buhay ay langit sa piling mo. Aming ligaya na pag may mga api, ang mamatay ng dahil sa'yo.
You may now take your seats. So again, good morning and welcome to the opening ceremonies of the 2017 APRU Global Health Program Conference. We would like to call on first to deliver the opening message on behalf of the University of the Philippines President Danilo Concepcion, the Executive Vice President of the University of the Philippines, and former Undersecretary of Health. Let's give a very warm round of applause to Dr. Ted Herbosa.
Thank you, Wendell, Dr. Trenawan, Melissa, Christina, all the APRU delegates from the different member universities, my friends in the international community in global health, of course, the faculty, the administration of University of the Philippines, the different campuses from Diliman, Manila, Baguio, and all the others that are here. Friends, ladies and gentlemen, good morning to all of you. To the participants of APRU Global Health Conference 11th Annual Workshop, from the experts, the researchers, fellow academics, as well as students, to the organizing committee from the Association of the Pacific Rim Universities, welcome to the Philippines. The University of the Philippines, as the country's national university, is honored to host this year's event. It is our honor to lead this year's local organizing committee. Our constant call to the UP community is to uphold honor and excellence. But these lofty goals are always rooted in the name of service. To most of you, doing research and generating new knowledge may already be second nature. These conference and workshops serve as an avenue to collaborate, exchange insight, and drive that pioneering research spirit even further. In particular, APRU's goal of harnessing the potential of Asia Pacific universities to tackle global health education problems is truly commendable in its synthesis with stakeholders such as policymakers and the media. This year, I am grateful to the APRU for allowing UP to host, given its relevant and timely agenda on drug and substance abuse, migration and health, reproductive health, mental health, and cancer. But my challenge to recalibrate these scientific marvels and refocus them on the less privileged and the marginalized. It is with hope that the projects in global health education, disease prevention, migration, and tobacco control will be replicable in local communities to reach the farthest edges of society where these initiatives are needed the most. May these conversations help craft local policy to institutionalize the good that will be produced over the next few days. Again, let me thank you for participating in this year's annual workshop and good luck to all the participants. Mabuhay po kayong lahat at magandang umaga.
Thanks very much, EVP Ted. Before we call on the next speaker, we would like to have a video presentation.
Today's challenges are too big and too complex to solve alone. No one person can cure cancer. No one country can clean up our oceans. And no one leader can end inequality. But when we work together, there's no end to what we can accomplish. We need to create opportunities for bright minds to come together and inspire each other, to bring together diverse insights and leading innovation to craft the new solutions we need for the socioeconomic and environmental challenges we face, and to make sure our leading institutions have a voice in shaping a sustainable and inclusive future. That's the ambition of the Association of Pacific Rim Universities, to be that voice of knowledge and innovation for Asia Pacific and the world. We connect the leading universities of the Pacific Rim and enable them to work together to address our society's biggest concerns. We foster engagement with government, leading to better policy. We cultivate links with enterprise, growing the impact of research. We are agents of change. We challenge assumptions. We bridge cultural divides. We bring new thinking to big issues. We are the voice of knowledge and innovation for Asia Pacific and the world.
So, friends, please give a very warm round of applause to the Secretary General of the Asia Pacific Rim Universities, Professor Christopher Tremawan.
Well, thank you so much, Executive Vice President Hubosa, for such a wonderful and warm welcome to us all. And may I, as Secretary General of APRU, welcome you all, our colleagues from the University of the Philippines, from the core group of the Global Health Program, distinguished guests and participants. It's wonderful to see so many of you here, and it's a privilege to address you all and to introduce a little about APRU. We describe ourselves in these terms of bringing together those who can think innovatively about the future challenges that we face. And so our aim is to bring together the minds of the major research universities around the Pacific Rim, government, business, community leaders, and to work closely on research, advocacy, and public policy. So we have quite a number of members. Many of you will recognize them. And together we work across the region in partnerships on various issues. And one of the other things that connects us is, of course, the common environment, the dynamism, diversity, and the challenges of living on the Pacific Ring of Fire, and all those issues that we face as societies around the Pacific Rim. We are based in China now. We are based in Hong Kong, on the campus of the Hong Kong University of Science and Technology. And from there, we're finding that we are able to coordinate across the Pacific with all our partners. And we see ourselves, as that video just said, dealing with the complexity of the issues by working together. No one university, no one country, no one government, no one corporation can solve everything. The aim is to work collaboratively so that we can accomplish many things. And so we work also with many partners. We work with APEC, we work with corporate, the United Nations, and we work with many corporate partners as well, fostering partnerships to try to innovate policy development and also growing the impact of the collective research of our members. Let me just share a few of the programs that we do. Obviously, the Global Health Program is one of our key programs. Begun in 2007, which was to advance all our contributions on global health. And I'm told that much of the agenda was driven by the interest of students in terms of saying that we need a healthy planet. It's not just dealing narrow issues of human health, but the relationship of all these issues of human health to what's happening to the planet as well. So engaging all our stakeholders in innovation, not only researchers, but also students and policymakers, as I've said before. And it has had many achievements in terms of, I'm sorry, you seem to be going too fast. Here we go. Here's the APRU Global Health Program. So it's provided as students with a platform to engage in competitions and to connect with policymakers and experts. It's created a distant education course to invite different perspectives and foster both innovation and global leadership. And it has, in research and advocacy, it has worked closely with policymakers. So, and we've had forums such as this conference working very much on these broader issues. And of course, I would like to thank, as in conclusion, again, our host, the University of the Philippines, thank USC for being the hub for our program on global health, and to thank all of you for coming and participating in what I think will be an extraordinarily successful event, and I wish you well. Thank you so much.
Thanks very much. We also have a video message from Dr. Jonathan Samet from the University of Colorado at Boulder.
Hello, this is John Samet, and of course I'm not with you today in the Philippines as this meeting of the Association of Pacific Rim Universities starts. Behind me is a scene from Boulder, Colorado, where I am moving to become Dean of the Colorado School of Public Health. And unfortunately, my very first week on the job is the same one as this meeting. I wanted to let you know how much I have enjoyed working with all of you, the group who have consistently contributed to the APRU Global Health Program activities, helped to organize the meeting, and the many, many, many colleagues and friends that I have met from a very impressive group of universities. I've enjoyed meeting your students and hearing about your work. The APRU Global Health Program has been a great success. It will go on. Melissa Withers has provided incredible leadership for the program, and with you at this meeting is my colleague and associate director of the Institute for Global Health at USC, Heather Whipley, who has been to many of the conferences, another key figure. So I wish you luck. I will continue to follow the activities of the APRU Global Health Program. And I hope that in the future, I will be able to come to the annual meeting. So I look forward to seeing you all again, and I know that you will have a great conference.
So thanks very much, Dr. Jonathan Samet, all the way from University of Colorado at Boulder. For the benefit of our friends and family here and overseas, if you have family and friends who would like to see you online, I would like to remind you that we can be seen through UPOU networks.upou.edu.ph. That's UP Open University. So UPOU networks, that's one word, .upou.edu or edu.ph. And now we will move on to the keynote speaker, and I'd like to introduce the keynote speaker. Dr. Curtis Harris received his Doctor of Medicine. So Dr. Curtis Harris received his Doctor of Medicine degree from Kansas University School of Medicine. He completed his clinical training at the University of California, Los Angeles, and at the NCI. He has held positions of increasing responsibility at the NCI. He received numerous honors throughout his distinguished career, including the Alton Ochsner Award relating smoking and health from the American College of Physicians, the Distinguished Service Medal, the highest honor of the United States Public Health Service, an honorary PhD from Nippon University School of Medicine, the AACR Princess Takamatsu Award, and the AACR American Cancer Society Award from Research Excellence in Cancer Epidemiology and Prevention. He is a fellow at the American Society of Clinical Investigation, the AAAS. Harris has published more than 500 journal articles, 100 book chapters, and edited 10 books, and holds more than 30 patents owned by the United States government. He also serves as editor-in-chief for the journal Carcinogenesis and has held or currently holds elected offices in the American Association of Cancer Research and the Keystone Symposium on Molecular and Cellular Biology. Dr. Harris has a wide range of accomplishments spanning molecular genetics and epigenetics of human cancer to molecular epidemiology of human cancer risk and mechanistic biomarkers of cancer diagnosis, prognosis, and therapeutic outcome. So, ladies and gentlemen, please give a very warm round of applause. Dr. Curtis Harris from the National Cancer Institute of the United States.
Well, thank you for that rather long introduction. It's a great pleasure to be here. I want to thank all of you for coming and giving me the opportunity to talk about precision medicine. The principle of precision medicine, I'll be discussing cancer, of course, but it can be used for the environment and chronic obstructive pulmonary disease, metabolic diseases, various kinds of strategies for investigation and identification of individuals who are at high risk. So the kind of medicine that I was trained in is shown here. It's traditional medicine in which one takes a complete history and then does a physical exam and determines signs and symptoms, and then some standard laboratory tests to develop a differential diagnosis. But precision medicine is multi-centric. It's individual, multi-layered, individual-centric, and interconnected. And it involves information commons that builds upon the epidemiology and traditional clinical medicine. So this shows you in a little more detail the information commons and the various omics, and I'll discuss several of those during my presentation. That leads to a knowledge network, and that network can then be utilized for improving clinical medicine, particularly at an individual level. And this also feeds back into the information commons. It also promotes and informs biomedical research, and this information, which is more mechanistic, also comes back into the information commons. And then finally, it guides prevention research, and which is a very important aspect of global health, of course. So let's first go to the expososome. And this was first coined by Chris Wild, who is the International Agency of Research on Cancer Director in Lyon, France, the WHO organization. And in addition to the external environment that we're all very familiar with, he proposed that there's an internal environment that's directly related to the external environment. For example, inflammation and obesity and other connections, and that this can lead to a improvement in cancer biomarkers of risk and prognosis. And feeding into this is the genome and epigenome, including cancer susceptibility, that provides an understanding of carcinogenesis that enhances the selection and use of biomarkers for risk diagnosis for cancer prevention and screening strategies. Obviously, the genome and the epigenome, especially the genome, is important for identifying drivers, excuse me, of the carcinogenesis process. And these are, in fact, these mutant genes in general are the blueprint for the malignant process and also are targets for cancer therapy. Chronic inflammation and infection can increase cancer risk, and I'm sure you're all familiar with this. It can be largely inherited versus acquired. Hemochromatosis and iron overload disease and liver cancer is a good example. Inflammatory bowel disease and familiar pancreatitis. The former president, Jimmy Carter in the United States, many members of his family had familiar pancreatitis and died of pancreatic cancer. For reasons that are not clear, he did not, and he's still alive in his 90s and is getting therapy right now for melanoma that's metastasized and looks like it's cancer immunotherapy, looks like it's being successful. More frequent than this are the acquired conditions. I've just listed a few examples of viral agents, bacterial agents, and parasitic agents that are associated with increased cancer risk, and you can add many more to that. And these together, global impact is about 2 million human cancers per year are related to infection. And this comes from the World Cancer Report from IARC that I and Jonathan Samet, a lot of other people contributed to. But does not include another category of chemical, physical, and metabolic conditions, such as acid reflux leads to Barrett's esophagus and increases the risk of esophageal carcinoma, obesity that's associated with multiple sites of cancer, smoking, of course, and arsenic, and there are a number of other agents, and I'll talk about the microbiome in a moment, that lead to increased inflammation and increased cancer risk. So these other causes of inflammation are associated with many more cancers per year, at least 6 million or more worldwide. Now let's go to obesity. Obesity is becoming a global problem, and that's one that's increasing over the last 2 decades. And there are 2 points of, I think, really significant observations made in obesity research. The first 2 are about 15 years ago, in which it was discovered that macrophages are found in fat. So in your body fat, there are many, many macrophages that can interact with the diplocytes and prediplocytes in feedback loops that lead to inflammation. Secondly, there are 2 other manuscripts that appeared about 5 or 6 years ago showing that diplocytes can become senescent. And when they become senescent, they start producing a number of inflammatory agents, IL-6, IL-8, TNF-alpha, and others that contribute to the inflammation. And there's also free radicals, nitrogen-based and oxygen-based free radicals, which are formed. Now, I mentioned the microbiota just a moment ago, and it's a very emerging area and exciting area in cancer research and research in other disease entities. The microbiota in the colon or the small intestine plays a very important role initially for maintaining the barrier of the mucus and the barrier function of the mucosa, and also it tunes up the innate immunity pathways. However, it can play a role in initiating and progressing disease, including cancer, and the various microbes can actually produce genotoxic agents that cause DNA damage and cause mutations. Many of them are pro-inflammatory and cause a inflammatory chronic inflammation. And some of the conditions that cause dysbiosis, which means a change in the character of the microbiota, in this case in the gut, include diet, Western diet, and other factors. It can also play a role in cancer by causing a biofilm that coats the surface in the colon, primarily on the right side of the colon. And this biofilm has many different inflammatory properties that are listed down here, including more inflammation. And lastly, the microbiota is starting to be shown, there's a nice paper in Science just recently, that it can actually metabolize and inactivate cancer therapeutic agents. And there's emerging evidence that it can also influence the immune system and influence cancer immunotherapy. So these are very interesting and important areas of investigation in the role of the microbiota. Now, I'm sure you're all familiar with chemical agents that have been identified going all the way back to the chimney sweeps and hydrocarbons causing scrotal cancer, aflatoxin from fungal infections of corn and rice, causing liver cancer, and then obviously tobacco smoke, which is, there's about 60 different chemical carcinogens in it. It's a witch's brew of chemical carcinogens, and several of them are quite carcinogenic, and combinations are quite carcinogenic. So let's go back to the precision medicine and go down to the epidemiology and some aspects of global health. I'll be talking mostly about lung cancer today for many reasons. One, it's the worldwide most lethal cancer in terms of number of deaths, and liver cancer is actually second worldwide. Now, in the United States, and I'll get to the global in just a moment, this is a table that comes out of the report of the Surgeon General in 2014. This is 50 years after the first Surgeon General report in the United States made really a diagnosis of smoking and health. And John Samet was one of the key people in charge of this. And they did a calculation not only of cancer, but chronic obstructive pulmonary disease and cardiovascular disease and even fires. And in the United States, over this 50-year period, the number of individuals with premature deaths, it's absolutely outstanding. It's actually terrible. 21 million people had premature deaths in the United States from tobacco. And of course, the tobacco industry claimed that it didn't have any effect, and for quite a long time. Now, one of the positive things that's happened in the United States and elsewhere is that anti-smoking campaigns have started. So, and this is lung cancer in males, and it's been going down, and females has plateaued off and maybe is about ready to go down. So in terms of protection against cancer, anti-smoking campaigns have been the most effective tool we've had to decrease cancer globally and in the United States. So this is the global trends I'm sure you're familiar with. And again, in developed countries, particularly in males, it's been going down. And in females, it's also probably is plateaued off. And I'd like to show this particular picture because this is smoking in men around the world, including the Pacific Rim. And the dark brown here is between 30 and over 60 cigarettes per day. And the United States used to look like this, used to be dark brown, but anti-smoking has had an impact here. And I will say that lung cancer is going to continue to be a problem, and chronic obstructive pulmonary disease from smoking and the atmosphere is going to be continue to be a problem in much of the world, including the specific rim. Now, one of the interesting phenomena that's happened in our clinics is that my training is in medical oncology, and in our clinics, when I was doing medical oncology, about 8 to 10% of the people coming in the clinics claimed they were never smokers. And now it's gone up to about 14%. And again, Jonathan Samet's written a very nice commentary about the pluses and minuses about these kinds of data and how real they are. And overall, it's a trend that I think is becoming convincing, at least in the United States. So what's causing these cancers? Well, one possibility is secondhand smoke or environmental tobacco smoke, or there are lots of different names, and you could choose the one that you think is most politically correct. And in 1981, this is a color from painting from Professor Hirayama, the late Professor Hirayama. This was a global health, world health meeting, and he presented for the very first time data that housewives of men in Japan who smoked had an increased risk of developing lung cancer. I will tell you, there were about 300 people at this meeting, and I would say probably half of them did not believe what he was saying. But he was absolutely right, as I'm sure all of you know. There's over 80 or 90 very convincing papers showing that secondhand smoke increases the risk of lung cancer. Well, I was sitting in that meeting and was thinking about how could I investigate this. And I'll show you the hypothesis in a moment. But since it was in Greece, and I happen to like some of the flowery language that Hippocrates and others have used, and this is, I think, quite appropriate for precision medicine. Some men have constitutions that are like wooded mountains, running with springs. Others like those with poor soil and little water. Still others like land rich in pastures and marshes, and yet others like the bare, dry earth of the plain. So physicians, even thousands of years ago, recognized that people differed from one another, and that some people are more likely to end up with a premature death for various reasons. So as I said, I was sitting at that meeting, and I said, well, how can I investigate this? And I thought about it, and well, what I wanted to do was to ask the question whether or not parental smoking, as shown in this hypothesis, that childhood exposure and genetic alterations and innate immunity increase lung cancer risk in never smoking adults. Well, I had to wait 28 years, almost 30 years, because women in the United States didn't start smoking until the Second World War. So their children, we had to have time for their children to actually develop cancer. And so we examined in 2 different cohorts with the Mayo Clinic people. And what we found was that parental secondhand smoke exposure during childhood is associated with dose-dependent increase in lung cancer risk in never smokers in 2 different cohorts. And this was especially true for those who had a haplotype of mannose binding lectin, type 2, that gives you a hyperactive innate immune system. So immunology, again, plays a role. And one of the most surprising findings was that these never smokers actually developed lung cancer in their 50s instead of in their 60s and 70s. So now let's go to the genome. There's been a huge amount of effort using um, uh, genome-wide mutational analysis. When I started oncology, the traditional view was a histology of squamous cell, small cell, and large cell. And in '87, KRAS mutations were discovered. And in 2004, EGFR mutations were discovered. And then in 2014, there's a whole group of mutations and fusions that are associated with increased risk of lung cancer. Now, this is somewhat misleading because almost all of these are in never smokers, not in smokers. So what is common in smokers besides KRAS mutations? Well, the elephant in the room is p53 mutations. So these bars, this is p53 mutations, and on the other axis on the other side is different kinds of cancer, and lung cancer is second in that list. So another aspect of p53 mutations is that there are two mutant types, those that lose function and those that gain oncogenic function. So p53 is an unusual tumor suppressor gene in the sense that it can switch from a suppressor to an oncogene, depending on where those mutations are. Does this make any difference? There are many different cancer types, and this kind of analysis has been done. In this case, lung cancer. And in the red line, this is a Kaplan-Meier plot, 100% survival, 0% survival. And this is a 5-year point down here. And there's a decrease in survival, even if you correct for stage and other risk factors that are associated with this gain of function mutations. As I said, this is true of many different kinds of cancers. So there have been three eras that seminal advances in environmental carcinogens and mutation of the genome have been found. The first, of course, happened in the 70s, and this is an example of rapid mutagenesis testing of chemical carcinogens by Bruce Ames and colleagues. And then a number of years after that, in the early 90s, our group and other groups discovered that p53 mutations can be linked to environmental carcinogens. In other words, different carcinogens leave a molecular genetic fingerprint in the p53 gene. And then more recently, Ludmila Alexandrov and Mike Stratton and others have used a more complicated algorithm to look at the whole genome for mutations. So let's first look at the old school way of doing it, and that's looking at p53 mutations and finding that alpha toxin exposure led to specific DNA adducts on guanine that led to mutations, and at a particularly interesting site at 249. And the 249 mutations are gain of function mutations. So people who have that mutation, for example, liver cancer, have poor survival if they don't. Polycyclic aromatic hydrocarbons and so on and so forth, ultraviolet light, CC to TT transition. Those link together the molecular biology of DNA adduction by chemical carcinogens and mutation type. Now, as I mentioned, the latest is studies that done by Stratton and colleagues, and using a very interesting methodology, an algorithm, non-negative matrix fractionation, computer analysis. And they have found that there are a number of signatures that are associated with exposure to tobacco smoke or alkylating agents, aflatoxin, and so on and so forth. And these actually match up quite nicely with p53 mutation. One of the things that Ludmila did was to compare a number of tobacco smokers matched with never smokers or non-smokers, and found that the signature 4, which is in blue, is predominant, and the number of mutations, this is megabase, that are found in the total exome of the genome in smokers is substantially higher than in the never smokers. Now, can you experimentally show that this is linked again, as we did with P53 mutations? And the answer is yes. So this is signature 4. This is exposure of humanized mouse cells with wild-type P53, same signature. And the very last panel here is human embryonic, human mammary epithelial cells exposed to benzpyrene. So there's a convergence of a signature in all of these that buttress the observation of hydrocarbons, in this case benzpyrene, causing this kind of mutation. Now let's turn to early stage lung cancer, and this also applies to many early stage cancers. There are a number of unmet needs. One of the revolutions in screening in lung cancer has been low-dose CT. And there are about 10 million people in the United States that are eligible for low-dose CT screening. However, the capacity to do that screening in this large population is nowhere near that. So there's a need to prioritization of people for low-dose CT. The second is if a lesion is found, and I'll talk about this, then we determine whether it's cancer or a benign lesion. And then lastly, if surgery is performed and the lesion is removed and it's shown to be a cancer, is it one that needs additional therapy, adjuvant therapy? Right now, in early stage cancer, that's usually not the case. So to go back to inflammation, and these are studies from our group over the last 10 years or so. In a prospective study, we found that IL-8 and CRP, C-reactive protein in the serum, was associated with an increased risk, even 5 to 8 years prior to diagnosis. This was done in a European American population because in these studies there weren't not enough, in these prospective studies, not enough Afro-Americans that were included. This actually has changed for the better right now. At the time of diagnosis, again, IL-6 and IL-8 were shown to be increased both in Afro-Americans and European Americans. And in Afro-Americans, this pro-inflammatory agent here and this anti-inflammatory agent, IL-10, was elevated. And survival is associated with a number of inflammatory agents. It's also associated with mannose-binding lectin, which is, I mentioned earlier, is innate immunity, TNF-alpha, and so on and so forth. So inflammation plays a role in all aspects of risk, diagnosis, and survival. So now let's ask questions about risk in more detail using other omics. And these are two of my colleagues who actually now, she's at the FDA and she's at the Ohio State University. And so this is tumor metabolism and metabolome. And the hypothesis is initially that unbiased metabolomics would discover biomarkers associated with risk diagnosis, prognosis, and therapeutic outcome of lung cancer. And in fact, it has. So this takes us back to Hippocrates again and analysis of urine. So apparently, Hippocrates and physicians of that age tasted urine for diagnosis of disease in his patient. Now, fortunately, when I went through medical school, I didn't have to taste urine. We had urinalysis for doing such a thing. But this is some more flowery language from a physiologist named Armstrong. From a liquid window through which physicians felt they could view the body's inner workings, urine led to the beginnings of laboratory medicine. So in these metabolic studies, in which we actually measured uh, 4 different metabolites in the urine, we found that that 2 of these, creatine riboside and N-acetyl nervinic acid, were able to refine screening decisions. And these are called ROC curves, so it's sensitivity and 1 minus sensitivity. And in adding those 2 metabolites in the urine to usual risk factors such as smoking, one comes up with a a cutoff of about 77%, specificity 87%, positive predictive value 75%, and a very important one for the clinic is negative predictive value, which and correctly classified by 84%. So that is a test that's in progress of being commercialized, and we think it will be of some use. Well, are these metabolites, for example, the creatine riboside, are they found in the tumors or are they found elsewhere? In fact, they are found in the tumors, and on the far left is the amount in the tumor versus the matched non-tumor portion of it. And then the far right is a regression analysis of the amount in the tumor versus the amount in the urine. And as you can see, there's a quite positive correlation coefficient in this kind of analysis. So we've done other studies, and I want to point this out because there's health disparity in some of these observations. And so this is the study of European Americans, and we found using multivariate analysis that the odds ratio, which are quite high, over 12, for creatine riboside and over 10 for the N-acetyl nervinic acid in European Americans. However, in Afro-Americans, it wasn't significant. So the question is why, and we're investigating that from doing mechanistic studies. So early diagnosis. I'll show you a couple of studies, not from our group, but from others. And this was asking the question again, is the lesion cancer or not? And one strategy is to look at sputum DNA methylation or at serum. And again, these are ROC curves, sensitivity and 1 minus sensitivity or false, as is shown here. So that's one strategy that's being explored. The second is to do really expression analysis in the nasal epithelium versus the bronchial epithelium. And this follows up some studies that Avi Spiro and others did. That's what's found in the bronchial epithelium in terms of expression analysis is also found in the tumor. So extended this to the nasal epithelium, and this points to what's called the field effect. That cigarette smoke not only leads to cancer in the lung, but it changes and increases cancer risk in other sites within the respiratory tract that they're smoking. Now let's end up with their surgical resection, and cancer is found, and then does this individual need or should we offer adjuvant immunotherapy? As I said, in stage 1 cancer, seldom is there adjuvant immunotherapy. What we traditionally have done is wait until the tumor recurs, and it does in about 1/3 of the individuals. And then we treat this tumor, this metastases, which may be several centimeters in size, with our traditional kinds of therapy. One hypothesis is that microscopic metastases may be more susceptible to therapy than if you wait until there's a larger tumor. So both immunotherapy and chemotherapy. So we've done a number of studies looking at the earliest stage of lung cancer, stage 1A is about 3 centimeters, and stage 1B is 5 centimeters and less. And the pathologist in these cases does not find any evidence of metastases in the lymph nodes or other part of the lung. But about a third of the cases or more have metastases that aren't detected. So in a couple of studies, we showed that there are 4 genes that are expressed differently in cancer versus non-cancer. And which we call the 4-gene signature. And that's shown here in both Japanese and in American patients. And the Japanese like to use relapse-free survival. Previously, we looked at miR-21, one of the microRNAs, non-coding RNAs that are associated with lung cancer survival. And the two of these together, as shown down here, are associated with poor survival. In the US population, it was more stage 1B cancers than 1A, and we traditionally prefer cancer-specific mortality. And as you can see that with the 4-gene signature, these are Kaplan markers, again, 100% survival, 0%, and this is a 5-year point. Poor survival, and miR-21 expression, also poor survival. And if you combine these, if neither one is high or a risk factor, fairly good survival. If either one is, if one of the two is high, intermediate survival. If both are high, quite poor survival. So what's the principle here? The principle is the following, and that is one can get, with a degree of accuracy, in this case, non-coding RNA and coding RNA, if you combine them, you find that there is a overlap that can increase the precision. And what you get is what was described before. If they're both low risk, very good survival, one's high, poor survival, if 2 is high, even much poorer survival. Why? Well, it's because most screening methods also misclassify some individuals. But in this case, they misclassify different individuals. So the non-coding RNA misclassified these individuals, and the coding RNA, the other side. So that's the, and we found that same principle for adenocarcinoma of the esophagus, the breast, and colon, and a variety of other tumors. So what happens if you add a third statistically and mechanistically independent biomarker? Does this improve the prognostic classification? In this case, we used DNA methylation. In a previous study by Esteller and colleagues in Spain identified 5 different sites of DNA methylation that were associated with poor prognosis in lung cancer, stage 1 lung cancer. I looked at those data, this is univariate analysis, and I said, well, we should do multivariate analysis to ask the question, are these all independent of each other, or are they all dependent of each other? And they were found to be all dependent of each other. So we just chose one of these, and that's HOXA9. And when we added that as a third biomarker, we found that the results were relatively convincing, both in the US population and in the Japanese population. If none of the 3 were positive, there's very good prognosis. If one's positive, intermediate prognosis. If 2 are positive, even poorer prognosis. And if all 3 are positive, even poorer prognosis. And these are the hazard ratios bottom you can look at. And all this has been published in the last few years. And to go back to the metabolome, we also found that combinations of metabolites that I just described are associated with poor prognosis. So if all 4 are elevated, that's the red line here, and this is a Kaplan-Meier plot, 100% survival, 0%, and 5-year point. And so right now we're adding this metabolome results with the other biomarkers to show that if they're statistically and mechanistically independent of each other. So let me end up with a problem associated with screening, whether it's mammography or in this case, low dose CT. And that's a high false positive rate. And it's 96% in low dose CT. 96% are false positive. So if you visualize that, say this is a concert hall, and you go through a number of scans of high-risk individuals, you're going to essentially find 3 people who have lung cancer. And you'll find lots of others who don't. So this is a serious problem in the sense of, is that lesion suitable for biopsy? About 2/3 are. Is a biopsy accurate in all cases? No. Should we do surgery in everyone who has a lesion with this amount of overdiagnosis? Surgery of the lung is a pretty serious type of surgery. And there are lots of side effects associated with that, including lethal side effects. So I went through some of the unmet needs associated with lung cancer screening in terms of prioritization, diagnosis of cancer or not cancer, and finally determining people for prognosis. And I'll end up with this. So this makes the point that even the earliest stages of lung cancer in which surgery is performed, there are people who are high risk and people who are low risk. And about 25% or 30% reoccur and die of the disease. So what's the role of precision medicine? Well, the precision medicine is to decrease the false positive rate, to increase the and decrease the financial cost, and also reduce the overdiagnosis and improve the diagnosis and identification of people who need adjuvant therapy. And those that are low risk, you observe. Those that are high risk, you offer them the opportunity for immunotherapy and cancer immunotherapy. So this is all an example of using precision medicine for lung cancer. And I made the point at the beginning, you could do the same for other cancer types or for chronic obstructive pulmonary disease or for obesity or a variety of other biologically complex diseases in which you want to focus down on individuals who are at increased risk of dying in most cases and having specific therapies for those individuals. So on the left are my colleagues over the last 8 or 9 years who performed many of these studies. And these are all very international studies. And that's a theme in our laboratory, and I'm sure in many of your laboratories. That's why you're interested in the Pacific Rim. And that's, I think, essential. And I want to thank you again for the opportunity to meet with you and tell you my story. Bye. Other questions? Yes? No? All right. I'll be around. You can ask me questions later.
Thanks very much, Dr. Curtis Harris, for that very illuminating presentation. Before we will temporarily halt the live streaming of the proceedings of the conference. Before we proceed to the break group photo and the Global Health Live course observation, I'd like to call on Dr. Melissa Winters, Assistant Professor at the University of Southern California, for a few announcements, please.
Hi, good morning, everyone. I just wanted to make a couple of announcements. So you'll see that if you're interested in dropping in on one of our distance education courses that APRU members are participating in, it's going on right now. So after our photo, you can drop in room Saison. And the other thing is in your registration packets, you got two important pieces of paper. One you'll bring tomorrow, which is the ballot for our voting on the global health case competition. So we are going to be screening the 3 videos, the finalists of that competition live here, and you all will decide on the winners. All 3 teams of students are present here at the conference, so you'll be able to meet them and watch their videos tomorrow afternoon. So please bring that. The other thing I wanted to let you know about is you also received a paper for a raffle that will be taking place tomorrow. We're asking you to recommend some colleagues, people that you know that might be interested in learning more about the Global Health Program. And so if you could fill out this form and turn it into the registration desk by tomorrow at lunchtime, we will be holding a raffle in the afternoon and giving away some fantastic prizes of t-shirts and other goodies. Okay, so please fill that out. Put at least 3 names down of people that you may know that might be interested that we can contact regarding the program. And that's all I had to say for now. So now we'll move on to the group photo. Thank you.